x7 equals to 0, etc., right? We do row reduction. More to the point, we do the Gauss-Jordan algorithm. All right? We find that that's row equivalent to the following matrix. Now just read row by row for me if you wouldn't mind. 1, 2.
0, 3, 2, 1, 0, 0.
Next.
0, 0, 1, 1, 1, 0, 0, 0.
Next.
0, 0, 0, 0, 0, 0, 1, 0.
Oh, phew, that was close.
They're all zeros except for the last one. And it's 1.
Oh, really?
Yeah.
Oh, man. Well, that's a bummer. Because what this last equation, this right here is death. This means the solution set is actually nothing. It's the empty set. It's this guy. Because this last row says 0 times the variables equals to 1. Which is no bueno. Now, the way we can fix this is to put a 10 here. Right? How many row operations now? 12? I would guess, I'm going to guess 13. Probably it's 12 again.
10.
Oh, 10! Well, interesting. All right, so how much did that change things? 1, 2, 0, 3, 2, 1, 0, 0. Still the same?
It's a 10 now. 10 on the end.
Oh, that's a 10?
The bottom is still 0.
Now this is 0, right? So the last row is all zeros. That's fine. That's good. So what the row reduction has actually shown us is the following. We started with what seemed like 4 independent, possibly independent equations, right? Row reduction has revealed, in fact, those were actually 3 equations. Genuinely independent equations. That's revealed to us by this row reduction. See, this last row is just the no, it's not even, it's just no, nothing, right? It's just zeros. It's no equation, no condition on the variables there. So this is the kind of thing Gauss-Jordan does for us, is it sorts out how many genuinely independent equations we have, which is really, I mean, it's fascinating that it's so simple in some sense. Yep. Pivots. So what are the pivot variables here? Pivot, pivot, pivot. E1, E2, E3. These are the pivot columns. So our custom is to write the pivot variables in terms of the non-pivot variables. These will serve as our free variables or our parameters. So this problem has parameters, solution set rather. I'll be rather uninventive. I'll use x2, x4, x5, and x6 as parameters.
Why did you choose them?
Those are the non-pivot variables. Those are the ones that are not the pivot columns. Now you're like, but I could choose different things to parameterize the solution set. Yes, you could, but our custom is to write the pivot variables in terms of the non-pivot variables. There's something called the linear correspondence which will prove this can generally be done. I'll just tell you what the linear correspondence says. It says you can always write any non-pivot column as like a sum of the pivot columns. But anyway, more on that later. But was it? Yeah.
I was just going to ask, if we can express this solution set down to all the parameters that we have to, or do we have to use all the parameters of the solution set?
Our custom is to write the solution set in terms of the standard non-pivot column, non-pivot parameters.
Right, but do I have to use all of them?
Yes.
Non-pivot parameters? Okay.
I mean, we're going to need all of them. Here's the solution set. All right, so let's see here. for example, what this top equation says what? It says x1 equals to minus 2x2, right? Where's the minus coming from? 3x4 minus 2x5 minus x6 plus 10. I mean, the equation has plus, it has all this stuff on the other side equals to 10. But, I mean, we're going to solve for x1 is the point. This is the pivot variable written in terms of the non-pivot variables.
Okay.
This is our custom. So, that is minus 2x2 minus 3x4 minus 2x5 minus x6 plus 10, comma. The next one's easy, x2, comma. I'll stack them like this if you don't mind. What's x3 equal to? Oh. See, x2 was a non-pivot variable, so we just put x2 equals x2. x3. Well, x3 is interesting. x3 is minus x4 minus x5 plus 0. Just to emphasize, this is coming from these two and the relation to the third column. What's next? Well, x4, good grief, x4, am I below where you guys can see? I should probably write this way if you don't mind. I know it's kind of bad. So we got x4 and then x5. And then what's the... Oh, x6, right? That's also a non-pivot variable, so these just appear as parameters. And then what's x7? Oh, actually, I can fit it in here. What's x7 equal to? That one's easier. 0, right? So these guys, such that what? Such that x4, x5, oh, I'm sorry, where was I? Such that x2, x4, x5, and x6 are real numbers. So there you go. Sorry, that one's kind of ugly to look at in that way. Let me rewrite the solution set over here so it looks prettier. So it's like, let's see, the first one's 10 minus 2x2 minus 3x4. I can't read. Minus 2x5. Should have brought my glasses. Minus x6. I put the 10 first because it just seems right. And then we've got what? x2 is for x2. x3 was what? x3 was minus x4 minus x5. Then we've got x4, we got x5, we got x6, and then finally 0. So this is the solution for x2, x4, x5, x6, all free variables. Now, one thing I can do, right, in the test, one thing I would not want to do. What I would not want to do is to actually ask you to do this row reduction. That would give me no joy. The likelihood any of you would get to the correct answer, or me also, is about nil. So then I would have to face the delightful task of trying to give you partial credit on who knows what it means. So how do I ask this question? Because I think what we did, the interpretation at the end is important. How do I ask this question without burdening myself with the task of sorting through all of your bad arithmetic? It's pretty simple. I tell you that the reduced row echelon form of, I call this thing, give it a name, some name calling. In fact, if I have any sense, I won't even give you this matrix. I will say that there's a system for which the reduced echelon form of the augmented coefficient matrix, this, is equal to that, and then I'll say, write down the solution set. Because that's the cool thing. You don't even need to know the original system, and you can still write down the solution set. One other thing I wanted to try to communicate to you guys in this lecture is the relation between the number of pivot columns and the number of parameters in your solution. The first example we did once we got past that complex nonsense was what? We had 3 equations, right? Remember? And we had 3 equations, and how many pivot columns did we have? 3. How many free variables did we have in our solution? We had none. We had 0 parameters in the solution. The solution was unique, right? Remember that? We had a unique solution. The second problem, this guy, we had how many equations? We had 3 equations, right? How many pivot variables did we have? I'm saying this the wrong way. My counting was coincidental. How many? I'm counting wrong, guys. Here's the observation. There's a coincidence of counting in the last thing I just said. So here's the observation. Number of variables for the system, right, is equal to the number of pivots plus what? The number of non-pivots, right? Which says that if you've got, if n is the number of variables, right? So if we call the number of variables n, and we call the number of pivots k, the number of parameters is what? It has got to be n minus k. In this example, we had n equals to 4. Let me just show you let me just, comment. So we had 4 equals to 3 plus 1. That was this example. 4 variables, 3 pivots, 1 parameter in our solution. This awful example, we had how many? We had 7 variables, right? And how many pivots did we have? 3 again. 3 is popular, right? So 3. And then how many? 4. 4 parameters. This is what's known as the rank nullity theorem. So this is called rank. And this thing is called nullity. The nullity is, for us, the number of free variables in the solution.
You said it's a theorem. Is there any reward for proving that one?
Well, it's almost obvious, right?
Yeah, but I'm just curious, because sometimes I hear there are rewards or stuff like that.
Oh, no, there's no reward here. This is just tilt, head, squint, look at Gauss-Jordan algorithm, the G-George. Yeah, we're done. I mean, that's it. I mean, no, it's not one of those. But I did have my linear algebra instructor over the summer. He did a couple of awesome things. Number one, he wore a polo shirt, and he had his belly would stick out just a little bit, which is just awesome. He was not fat. He just, it's just style. So I enjoyed that. The other thing he did, which I enjoyed immensely, was he gave tests back in the order of the grade, highest to lowest. So, people around me would be going, "What did you get?" "Oh no!" And then the dread would grow as tests were handed back. It was fantastic. I've always wanted to do this. I just never have enough time to get around to doing it. I'm against it. I'm totally for it. I'm all for public shaming. It's not exactly public shaming. It's kind of anyway. And then the other thing he would do is he would sporadically give extra credit things. And then sometimes they would have varying degrees of if you can solve this, it's worth 5 points. Or if you can solve this, I should give you an A in the course. if you can solve this, you can have a professorship at a university of your name. If you can solve this, it's worth $1 million. I mean, there was like this list of things. But I don't have that for this course. Fun thing, it was fun. Anyway, I shut up. Sorry we got started a little bit late, so I ended a little bit late. But I will, again, remind you, if you missed last week, please do look at the YouTube so you can catch up. Or just work homework problems. That's also good.
Is the homework
What's that?
open right now? Like, is it linked to the last syllabus of the class that we already have, or